Representation theory is a branch of mathematics that studies abstract algebraic structures by representing their elements as linear transformations of vector spaces, and studies modules over these abstract algebraic structures. In essence, a representation makes an abstract algebraic object more concrete by describing its elements by matrices and the algebraic operations in terms of matrix addition and matrix multiplication. The algebraic objects amenable to such a description include groups, associative algebras and Lie algebras. The most prominent of these is the representation theory of groups, in which elements of a group are represented by invertible matrices in such a way that the group operation is matrix multiplication. Representation theory is a useful method because it reduces problems in abstract algebra to problems in linear algebra, a subject that is well understood. Furthermore, the vector space on which a group is represented can be infinite-dimensional, and by allowing it to be, for instance, a Hilbert space, methods of analysis can be applied to the theory of groups. Representation theory is also important in physics because, for example, it describes how the symmetry group of a physical system affects the solutions of equations describing that system. A feature of representation theory is its pervasiveness in mathematics. There are two sides to this. First, the applications of representation theory are diverse. In addition to its impact on algebra, a representation theory illuminates and generalizes Fourier analysis via harmonic analysis, is connected to geometry via invariant theory and the Erlangen program, has an impact in number theory via automorphic forms and the Langlands program. The second aspect is the diversity of approaches to representation theory. The same objects can be studied using methods from algebraic geometry, module theory, analytic number theory, differential geometry, operator theory, algebraic combinatorics and topology. The success of representation theory has led to numerous generalizations. One of the most general is in category theory. The algebraic objects to which representation theory applies can be viewed as particular kinds of categories, and the representations as functors from the object category to the category of vector spaces. This description points to two obvious generalizations. First, the algebraic objects can be replaced by more general categories. Second, the target category of vector spaces can be replaced by other well-understood categories. A representation should not be confused with a presentation. Definitions and concepts. Let V be a vector space over a field F. For instance, suppose V is Rn or Cn, the standard n-dimensional space of column vectors over the real or complex numbers respectively. In this case, the idea of representation theory is to do abstract algebra concretely by using n times n matrices of real or complex numbers. There are three main sorts of algebraic objects for which this can be done: groups, associative algebras and Lie algebras. The set of all invertible n times n matrices is a group under matrix multiplication, and the representation theory of groups analyses a group by describing its elements in terms of invertible matrices. Matrix addition and multiplication make the set of all n times n matrices into an associative algebra, and hence there is a corresponding representation theory of associative algebras. If we replace matrix multiplication Mn by the matrix commutator Mn minus nanometer, then the n times n matrices become instead a Lie algebra, leading to a representation theory of Lie algebras. This generalizes to any field F and any vector space V over F, with linear maps replacing matrices and composition replacing matrix multiplication. There is a group GL of automorphisms of V, an associative algebra ENDF of all endomorphisms of V, and a corresponding Lie algebra GL. Definition: there are two ways to say what a representation is. The first uses the idea of an action, generalizing the way that matrices act on column vectors by matrix multiplication. A representation of a group G or algebra A on a vector space V is a map with two properties. First, for any G in G, the map is linear. Second, if we introduce the notation GV for phi, then for any G1, G2 in G and V in V, where E is the identity element of G and G1 G2 is product in G. The requirement for associative algebras is analogous, except that associative algebras do not always have an identity element, in which case equation is ignored. Equation is an abstract expression of the associativity of matrix multiplication. This doesn't hold for the matrix commutator, and also there is no identity element for the commutator. Hence for Lie algebras, the only requirement is that for any x1, x2 in A and V in V, where x1, x2 is the Lie bracket, which generalizes the matrix commutator Mn-nanometer. The second way to define a representation focuses on the map phi sending G and G to a linear map phi VV, which satisfies, and similarly in the other cases. This approach is both more concise and more abstract. From this point of view, a representation of a group G on a vector space V is a group homomorphism phi GGL. A representation of an associative algebra A on a vector space V is an algebra homomorphism phi ENDF. A representation of a Lie algebra on a vector space V is a Lie algebra homomorphism phi AGL. Terminology: the vector space V is called the representation space of phi, and its dimension is called the dimension of the representation. It is also common practice to refer to V itself as the representation when the homomorphism phi is clear from the context, otherwise the notation can be used to denote a representation. When V is of finite dimension n, one can choose a basis for V to identify V with Fn and hence recover a matrix representation with entries in the field F. An effective or faithful representation is a representation for which the homomorphism phi is injective. Equivariant maps and isomorphisms: if V and W are vector spaces over F, equipped with representations phi and psi of a group G, then an equivariant map from V to W is a linear map alpha VW such that for all G in G and V in V, in terms of phi, GGL and psi, GGL, this means for all G in G, equivariant maps for representations of an associative or Lie algebra are defined similarly. If alpha is invertible, then it is said to be an isomorphism, in which case V and W are isomorphic representations. Isomorphic representations are, for all practical purposes, the same. They provide the same information about the group or algebra being represented. Representation theory therefore seeks to classify representations up to isomorphism, subrepresentations, quotients, and irreducible representations if is a representation of a group G. By defining phi to be the restriction of psi to V, is a representation of G, and the inclusion of V into W is an equivariant map. The quotient space with V can also be made into a representation of G. If W has exactly two subrepresentations, namely the trivial subspace 0 and W itself, then the representation is said to be irreducible. If W has a proper non-trivial subrepresentation, the representation is said to be reducible. The definition of an irreducible representation implies Schur's lemma. An equivariant map alpha VW between irreducible representations is either the zero map or an isomorphism, since its kernel and image are subrepresentations. In particular, when V equals W, this shows that the equivariant endomorphisms of V form an associative division algebra over the underlying field F. If F is algebraically closed, the only equivariant endomorphisms of an irreducible representation are the scalar multiples of the identity. Irreducible representations are the building blocks of representation theory. If a representation W is not irreducible, then it is built from a subrepresentation and a quotient that are both simpler in some sense. For instance, if W is finite-dimensional, then both the subrepresentation and the quotient have smaller dimension. Direct sums and indecomposable representations. If and are representations of a group G, then the direct sum of E and W is a representation. In a canonical way, via the equation, the direct sum of two representations carries no more information about the group G than the two representations do individually. If a representation is the direct sum of two proper non-trivial subrepresentations, it is said to be decomposable. Otherwise, it is said to be indecomposable. In favorable circumstances, every representation is a direct sum of irreducible representations. Such representations are said to be semi-simple. In this case, it suffices to understand only the irreducible representations. In other cases, one must understand how indecomposable representations can be built from irreducible representations as extensions of a quotient by a subrepresentation.